executions. So because probably those who have attended my session on last Thursday, you would have got an idea about how our NI Elvis hardware can help us in using a remote lab. I have discussed in detail how exactly we can use with configuring our modules with network, how we can have our hardware items in a group so that we can conduct lab experiments. So this is another product similar to NI. So this EMONA hardware is also a part of National Instruments academic section. So we have a tie-up with EMONA and National Instruments so that a few lab solutions we can make it with Elvis, few lab solutions we can make it with EMONA. So this EMONA hardware, we have it as a EMONA TIMS, which will be easy for our, what could I say, the remote lab totally. If a student, he has his laptop, if he's just connected to internet, so we can have a hardware, and that hardware also will be connected to an internet, where we can easily do it. Nearly 30 students, we can have a simultaneous experiments connected and doing on. Whereas if you see over there, when we try to do a remote lab, we need to conduct it as same as the regular lab, how it happens. So here we have a hardware which is a TIMS module, which helps us in doing this remote lab for multiple number of participants at the same time. So that we can have all our hardware connected with the instructor, along with I could say as a students also, because both the instructor and student both will be available at the same time, so that if you see over there simultaneously, whatever we need to plan for our lab experiments, we could easily schedule it in that way. So probably I could show you so how exactly we can make on things here. So I'll just share my screen so that you would understand how this EMONA modules will look like and where we can move on. Sir, could you see my screen? Can anyone reply whether
Yes,
my
sir.
screen is visible? Yeah, great. So now let me go for
Yes,
this
sir.
EMONA module.
Your screen is
So
visible.
now, yeah, great, thanks. So if you see that, this is what we have as a EMONA module. So where we have a single hardware can be connected with multiple devices or multiple students. So almost nearly 30 students or even more can be connected simultaneously, and we can use for it. So this EMONA TIMS module we have for different lab purposes we have. So one we have for circuit theory. So one we have for digital circuits, digital electronics lab, and one for op-amp for linear integrated circuits lab we have, and one for normal basic breadboard connections with basic experiments we have, and one we have for this SDR modules we have. So even with this also we can work on SDR hardware. So here, if you see, we have different modules we can use with it. This is something as a module by module, as multiple instruments are connected in a single box. So we have a single box unit where we can work with it. So today we will see some demonstrations also. I'm also going to handle this particular hardware demo totally on remotely, because these modules, if you see over there, this NetTeams free wire module, without any wire connections, it is purely, it's going to be internally module wise switching will happen. So in this, if you see, this hardware is present in Australia, so where we will be communicating to that hardware with the login details. So once if we have the same setup in our lab in our college campus, so where there also we can have the same setup, so where we'll be using it for the same regular activities by providing every individual student the access with the login access details there, username and password, the respective there. So now we'll get into these modules, how exactly it will look like, where exactly we'll use for it, what are the different hardware modules we have. Yes, we will see that one by one now. So now why we need remote engineering labs now. See, uh, as we all are aware of it, we are in the pandemic situation, and moreover, India stands top in the list. And here, if you see there, we have to provide proper uh, awareness about the pandemic, as well as we need to look into a community or a student sector where we are not even seeing them. It's almost for past 1.5 year, almost a past 1.5 year, we have not seen any students over there in person. So whereas our regular activities has to go on, and if you see over there, every research work also, whatever they are planning to do over there, even that also has to happen. So how exactly we are going to bridge this gap? See, earlier there is a gap between industry and academy. So where a lot of industries are trying to provide some lab related solutions where they can bridge between what are the recent or advanced problems that industry is facing to be solved by the academic. Whereas now, if you see over there, every one of us has been distanced among ourselves with, where we don't have any connections with each other with respect to a real-time hardware interface and how to conduct a lab, where a student will get confidence and how do they do their regular coursework. So everything comes into a question mark here. So how exactly we are going to solve this gap? Because it's now it is something I can say it as a gap between a student and a classroom, or a student and a lab. So how we are going to solve this gap? This is the problem what we have now. So probably when we want to address this issue, so how could we can do there? See, most of the places where we try to do it is, we'll try to access them with an online classes, we'll try to solve their queries. If I could see, most of the classes or most of the queries what we have is, how exactly we are going to serve a batch of students of 60 or 30 students in a 1 hour or 1.5 hour session. So how we are going to talk to them, or how we are going to uh, reach out to them and solve their queries in over there. So now if you see over there, we all have a time limit of work frame from 8 to 9 hours of work. How we are going to solve that? We need to have some system to work around the clock, so that we can help the students, or we can provide a different time slots where we can adjust multiple people to come and work. So the one thing where we can do it is, we'll try to have our entire lab, or we can have our entire classroom in a remote form, which is functional 24/7, so that we'll find time, and we can also find our convenient way of working with the lab hardwares. We'll have the interest to learn with this whenever we feel free, and we can try to access them. So how to create with that? So this EMONA is one of the place where we can do that easily. So if you see over there, this is what we were discussing about. So where the research work, where the scientist whoever wants to control with the spacecraft, they are also using with remote where there is no interaction between them. So for example, if you see there where the production work happening in a factory where the engineers are, everybody is in work from home now. So how they are controlling their factory units, where from where they are giving commands or controls. So now most of the industries they are talking about complete automation. So how exactly if they make entire factory as an automation, how could they achieve this? Because there won't be any person here. For example, if you see that Airbus got into the place where we have a complete automation there. So if you see there, many of the production units as the BMW or Mercedes, they all have come into the place where they can have their complete automation related their productions they have started. So when you want to talk to a machine, so it need not to be you have to be literally present over there. So you can be anywhere and you can access to that machine. You can talk to that machine in a remote form. So that's what we all now got into the place where we have these IoT elements there. So now we need to have our lab also to be a part of an IoT system. So that how exactly a factory production unit works, the same our regular college lab also has to be there. So that how engineers in industry can communicate to the lab works, how exactly our students also can talk to the lab experiments there. So how exactly they do it. So now those things would be done with the help of these three different options. For example, if you see there, earlier we used to have everything as a hands-on experiment. We'll have that, we'll have our breadboard, we'll have our all traditional desktop instruments on our table, and where we rig up all our connections, where we troubleshoot it, and then try to do it. So now, after some time, we got into a simulation platform. Before we go to the lab, we will learn the concepts with the help of simulation software. So these simulation softwares will help us in understanding the concepts of the experiment which we are trying to do. So these lab experiments can be addressed little earlier, or it could save some time, or it could provide some more insight about the experiments what we do with the help of this simulation. So now I could take something in a remote controlled experiments. I try to take some help from the simulation software also. So now if you see over there, we need to understand one thing very clearly. There is a difference between a remote controlled experiment. Sorry. Sorry. So we need to understand the difference between a remote controlled experiment and a simulation experiment. See, the simulation hardware is, or simulating through a software is something without no hardware, without no real-time parameters, without no real-time access. We will be doing something as a regular experiments. So this can provide something similar to the real-time word output, but this won't be the real signal. So because it is a purely simulation understanding, we will not have any information in it. Whereas when we go to a real-time hardware remote control experiments, there will be a lot of precautions, measurements we need to take, because if you see over there, in remote controlled experiments where we need to be everything to be controlled, whereas if there is a voltage variations, or if there is anything as a physical connection making, if there is any one particular switch or a relay unit doesn't work properly, then we could not switch to the next experiment. So how exactly this will be addressed is, we will have every system experiments are connected into a module, so that will be controlled by a software. There we will be working with the real hardware, because here if I turn off this hardware, we will not get any data, whereas in simulation it is not as that. because simulation will definitely get an output. So one advantage of having the real-time hardware on a traditional practice to the new lab resources, this lab resource or this lab can be open 24/7. This lab can be open for 24/7, which is very important for to set up a remote lab. Second one, so now we need to have access and control to this lab hardware or lab experiments list, because we are going to give this to a 30 plus or more number of students to access at the same time, so that we need to split this hardware. We need to have access to these devices everywhere or every time wherever they have internet they can access with it. So how we are going to use it, because this is the one which everything works on a internet browser. So now your IoT modules where you are trying to work with your production unit, you need to control your entire production with your IoT. The same way, I'm conducting my lab through an IoT model. So here the things will be the lab instrument or lab hardware. The purpose is to get students or academicians connected with their lab or research activity. The third one is make the lab or a hardware available 24/7. So this is what the major idea. What do we have now? So now one good thing is, so where exactly you can do it is, so this one provides a hands-on experience, so where you can do a lot of lab programs into it for different lab experiments. For example, if you see there, one device can work for one purpose. For example, if I take a circuit theory unit, so I can conduct a circuit theory related labs, so where I'll have a different inductor capacitors, and where I plan for different transformer related operations. I can try to do it. Yes, I can measure different current or voltage values with that. But if you see over there, I'll be restricted to do only an electrical coursework there. So electrical related lab I can do it. So for example, if I take something as an SDR module, so where I'll be working only on an RF part. So each and every module restricted with minimum lab experiments of 20 to 25 lab experiments you can easily do with that. So now this is the one. So for example, if you see here, so here we have a hardware. This hardware is connected to an internet. So where this modules, everything we can access through a browser. So this browser elements will have a direct interaction with this hardware, which is available in our lab unit or in our college server. So where it is connected with the internet, we can access through them. So the same way how you have the Elvis module connected on the top of it. So different top boards you can connect, whereas this baseboard remains same. So now if you see this top board, one may belongs to our digital electronic circuits. So the same way we have for circuit theory. So we have for different module for SDR. So we have one for free wire where we can do our basic experiments we can do with that. So now if you see over there, this is the units what we have. So if you see there 1, 2, 3, 4 EMONA TIMS unit where we have, and if you see there all are different modules which we connected to it. So one we have a normal breadboard. So one we have a circuit theory board built on top of it, so that we can have different experiments connected with this. So these 4 hardwares are available everywhere, which means if I have internet, I can access anytime. So this is present at Australia at EMONA Instruments Lab. So where we can communicate with this now when we are doing a demo. So the same kind of setup we'll be doing it in our college premises with the different lab purposes. So this is something your trainer kit board where you can connect from the signal source to the module. So that module output will be connecting to the oscilloscope where you can see the signals there. So now if you see that, this is what I was explaining you about. We have a different modules. So where we have one for circuits lab, one for circuit theory, and where we have for different transistors, where we have for op amp, and one for digital logic boards. So if you see in it, so this one on the top we have for SDR applications. So this helps us with higher end of RF modules where you can work on SDR related operations. So even this is for the basic fundamental of experiments where we can do it. These are the different lab elements what we have here. So now with one module, if you see there, this 24/7 365 days you can continuously you can use with it and you can carry on. And this is one advantage where you have. And if you see, this one hardware is equal to your maximum number of your, I could say it as your multiple function generator, oscilloscope elements you can use with it. So now if you see there, I'll go with the different modules. So where exactly you can do that is how exactly you'll conduct this. So for example, here I have a parameter where I can first what module I have to choose there. Excuse me. So whereas here, if you see, I have small units here. These units where I have to choose what device I need to use here. So I'll have multiple devices where I'll be using there. So I'll show you the demo from a EMONA place. So where we can do that. Do you see here with the help of this FreeWire NetTims module, we can conduct these many kinds of labs and experiments we can do with that. So that we can plan for our lab experiments based on our syllabus what we have here. So where we have a lot of modules, and if we have any, I could say it as a mathematical model. So how we want to plan that also we can do of our own, because here also we will be having a basic function generator, multiplier, adder, multiplexer, and noise signals, filter units. So here also we'll have them so that we can conduct several labs in it. So now, 1 minute, let me open up with your EMONA module there. So do you see over there here, this is the EMONA module. So these are all modules where we will be connecting for SDR applications. So in EMONA, if you see that you have a curriculum, so this curriculum will help you about to plan for your own syllabus, and you have an access for sample manuals. So if you see over there, here you can provide your email ID. So you can get for your temporary password, you can request for it. So once you request for your temporary password, you can provide information, your email ID. So from EMONA teams, they will share you a temporary password where you can access for the different manuals for different lab experiments where you can do it. So how exactly you can use for your IoT lab. So where you can see for your net circuits lab. So where you can have your digital logic labs. So you can easily plan for it. For example, if you see, so this is for one basic lab where you can use for your telecommunication purpose. So this is for a telecommunication lab, and where you can go for different coursework, how exactly your digital communication you can plan with it. So how exactly these modules can help you with this. And here they'll give you a lot of materials also with that, and the example programs also you'll take. For example, if you see here, in this, I can plan for my own TIMS 301 advanced lab teaching. For example, if I go for advanced lab teaching modules, so here, so where here you have a lot of videos, it will tell you about where you can do with this. So here in this, if you see that, you can go to the experiments list and where you can see the lot of experiments involved in it. So for example, no, it is not opening. So where here you could really do a block diagram based experiments. Uh, Give me a moment. Let me share my screen after taking that remote access. 1 minute. Uh, Sorry about that. So here for the free assessments, whatever we plan for it. So we'll go for the basic experiments. So what are the different experiments that we can do with this? So now, if you see there, here we have 4 different lab options we have. So for this lab options, first let me choose free wire. For free wire, I'll just have our own password for it. Okay, so let me hide for it. It's okay. So now in this, I'll just enter to the free wire experiments. So this is totally happening through my browser. So we don't have anything connected with me. So I'll go for start experiment. So if you see there, so how to make connections, so where to click on input or click on the output, or how to remove connections. So everything they'll mention over there. So to make connections, very simple. Output to input. To remove, you can double click the terminal. It will remove the connection. So here in this, how to choose a module or how to give connections, everything is provided in a manual very clearly there. So let me start with a simple one experiment there. See, for example, I have this module running here continuously now. So this is the time what we have. So today's date and today's time. So what we have in this. So now here I have a module. So where I can check with different time-based options of my oscilloscope. See, the signal is running over there. So this is the real data what I'm taking, and here what are the units I have for this. Do you see over there the divisions got changed? So earlier there were 2 divisions, 2 voltage per division. Here it is changing automatically because this is happening manually as per my access. It is changing there. For example, here I need to choose a module. So where I have to add a module, I have to choose it. For example, let me take a function generator here. So now if I take a function generator, so for this function generator, how I need to wire? So this sine signal or square or triangle I need to choose. So this sine output, I want to connect it to channel A. So now, once after I connected there, if you see my module, whatever I'm planning here, it is a real data because there is no frequency here. So once I start increasing my frequencies there, you could see it will respond to us properly. So frequency is there, but no amplitude. So I increase my signal amplitude so that what happens is we'll get our signal. So for example, I remove this terminal so I don't have any data. So this is the real signal where we are generating there. So now I'll go for a higher amplitude. So I'll change this to a square, triangle, half sine wave, some noise signal, a general sine signal, so I can move on. So now I'll make it as 1 volt. So now I have my signal with me. So now I need to add something as a some noise, or I can say it as something as a signal noise to be added. I need to apply some filter. So how could I do that? So for example, I have a noise generator and adder. So I'll take this is a noise generator and this is a noise adder. For example, this signal, I give it to here. This output, I'll connect here. So now if you see there, we have a signal with no noise. So when I added noise to this, do you see there? The noise has been added to the signal. This is an input signal and we have a noise terminal. No noise has been added earlier. So when I remove, this is what I got. So now what I do here is I try to add a noise. Actually, I want to show you a different unit. Sorry, with one. So this is the same signal what we have with the phase shift. So now I need to add little low noise to it, which means the noise floor is less. So now you could see that the noise has been added there. So now I want to apply a filter. So how could I apply a filter in C? So for example, I need to choose one more element here. Something as a utility. So now here a utility, I have something as a comparator, I have a rectifier, I have a diode and a RC low pass filter there, or I have a simple low pass filter there. So now what I'll do is the output coming from there, I'll connect it to the RC filter input. The filter output I connect it to the channel C here. So now the signal is filtered and we are getting it output there. So now if you see this one, so we have a proper signal with no noise, and we have a noise added to my signal, imposed it. Then that noise has been removed and taken from here. So for example, if I remove it, if I try to add little higher noise to it, then you could see where the noise elements have been added to it. So now you can easily save this data. So you can load this data easily. So you can have how good you can monitor with it. You can easily do it. So this is something, if you see there, I'm adding some good noise with that. For example, I'll change it as a 2 unit, so we can easily see the things clearly there. Yeah. So we have a noise, and the noise has been removed from a signal. So if you see that, this is simply simple as a signal parameter experiment where we can do with it. So now the same logic which we can do it is, we can do it with our rectifier operations there. So for example, how we could do the rectifier there. So for example, I have an input on this line, channel A. For example, let me remove this wire, channel B and channel C. I'll remove this. So there is no noise added to it. So signal input, I connected to channel A. The same signal input, I connected to diode as a rectifier there. I have a rectifier unit. So rectifier output, I'll connect it to channel B. So now I have a half a rectifier here. So when we try to add a higher frequency, obviously it will get updated with that. 1 unit per divisions, and then another module there. So now if you want to move this and you want to keep there and you want to access them, so for example, if you want to trace the data, so here I got downloaded. So now if you see over there, when I open it, I'll get these two informations there. So you could easily check with your signals there how exactly these modules can be visualized and how exactly you can conduct your real informations. That will be really easy for you. So now see, do you see that this particular point signal which I'm taking, and here when you click on this element, so when I move there, so only that particular axis where I'm tracing there. So when I take this part, it is totally no data are there in it. So for example, if I take this entire portion for my demo, then I could see what would be the frequencies there and what would be the voltage added to it. I could easily check with them. So this is something where I could take things easily and you can do it. So you can refresh it. So where each and every time there will be a new data you can add with that. So then, for example, we could go on to the different labs we can add with this. So this is for one module. And for example, if I go to the digital logic experiments, I'll open with another one. The screen may looks as the same, whereas if you see there, the modules what we choose will be a different one. So for example, if you see there, I want to have something as a signal generator, or I want to have something as a source of data. So how would I can have it? For example, if I say something as a binary counter, or for example, I can say this is a switch. So whenever I say on or off, so based on that it should work here. So here I'll be adding an OR module. So here I'll give one input to here and then another input over there. The result I connected to channel here. So now I'll say input is on. So this channel is high. So obviously it will be high. So the other channel is high, it will be high over there. So when I'll say low, it will become low. So how could I can visualize that? Then you have to have your signal connected with this, and you have to have a signal connected with here, which means I'm connecting multiple elements there. So when one element is high, the other element is also high. So obviously my output also will be a high. So here instead of going with a switch, so for example, if I say as a source of signal, for example, if I say instead of this, if I say as a source of signal, uh, 1 minute, yeah. So if you see there, when I connect this to here, you could see there is a pulse. You could see there is a pulse there. So now I'll connect two signals there. I have to connect this input and then another input over there. This output I connect to C. So now what will happen is, whenever this side is high, we have a high over there. Whenever our element is low, we got completely low over here. So this is something as a Boolean operations where we could show them in it. So here it's of different clock rates where we are seeing it. Basically, this is very similar to your truth table where we can explain things there. So how exactly you can choose this switch, where is a high and low there. The same way you could use with the signal source, and you can check with this. This is for one simple example of your digital labs where you could use. Or here also you can choose with your OR module. See here you see a dual NAND module or a triple AND module or a quad OR module. It's something as depends upon your four elements where you can connect and you can see output there. So when you want to have more number of inputs, so based on that you can choose. So where I can have a flip-flop, so where I can have a half adder and a SR flip-flops. So based on that I can have different elements or different experiments I could do. See, these things are happening in real time. Today's date and time is running over there. If I remove any one wire, I'll not get the data. I remove this wire from there. So when I remove that wire, I'll not get any input there, information over there. So this is something as what we are trying to show them in a real time. So when I connect this input to the source, based on that the things are happening. When I'm not connecting this source over there as an input there, then what happens is the second input is same as my output there, because there is no first input. Based on the first signal there is no output there. Whatever I gave as an input I'm getting there. So when I remove this wire, I should get the first input as there. This is something as 1 0 0 1 1 1 you can easily make. So now only input on the one side, I got the first input. When I connect this to the second one, the combination of it I'm getting output there. So when there is no input on the first line, I'm getting only the B line there. So this is something where we could easily showcase it and clearly explain to them. And if I share this same username password to students also can do simultaneously with it, because this is the ID. What do I get for my user VI? So for example, if Manimaran has a separate user ID, so he also can simultaneously access the lab over there, and he also will be doing it. So after doing all this work, he can capture it. So where he can capture and he can save for it. Currently save the screenshot what I have selected. One. So it has been saved there. So sorry. So where I can load it, where I can save to the previous one, save to it, and we can continue to it. So here when I say trace data, again I can capture this entire element there. So now I'll go and show in a folder. So 2 times I have captured these values there. So now if you see that, what would be my time and what are the channel informations I have got in it. So those informations I have taken in this. So how many number of samples that we are measuring? So those number of samples we have here. It's a real-time data what we are measuring with this. The same way where we can have circuit theory lab and op-amps lab. So now if you see, so I have the circuit theory lab. So where I have a voltmeter or source meter. So for example, I'll say a function generator. I have capacitors. I have a resistor. So I connected to it. So for example, if you want to make any connections with this ELC network, so you can easily plan and you can take outputs with this. So I have a current source. I have a magnetic coupling. So where you have different coupling units you have in it. For this, is it the same one? All right. Yeah. So this is for the op-amp one. So now if you see there, so I have access to this 4 lab activities. So where I'm working on a circuit theory lab. So where I can work on an op-amp lab, where I can work on a digital logic circuits lab. So where I can work on my basic experiments lab. So for example, where I have this noise, sorry, this is my signal, noise added, output to channel B, input to channel A, input to rectifier, so now if you see there, we have one experiment running continuously over here. We have one more experiment for digital labs running there. So whereas here also, when I change my frequency to it, when I change some amplitudes with this here, when I change different switches there, I could see the difference in my outputs there. So I remove one switch. I connect one switch. So now this output I'm not seeing. So it's a pre-built connection there. I'll change to a square input. So if you see over there, if I give some noise, so based on my inputs, if you see there, my output or my program is executing there. So now in this is something I could say it as based on my response, the experiments are happening immediately there. So when I open up all my switches, So here, based on this resistor values, we'll be getting the differences in the signals there. So now I have 4 different labs running parallelly. Simultaneously, I'm conducting experiments. So I could say as 4 students are working with me, the computer or the devices are as it is. For example, I could say as this way. So this 4 devices, I'm accessing every individual unit with me now. So where I'll be working on 4 different lab experiments there. So now this is one really good way where we can conduct a lot of real-time experiments with us. Hope you got some idea about remote lab, how we are developing with this. Any queries you have?
Dear participant, if you have any doubts, queries, you can ask now.
No doubts or queries?
I think no, sir.
Okay, fine then. I'll continue. So here, for example, what I could do it is, so now I'll just uh, share a few informations about your TIMS here. See here, TIMS, we have long-term associated with national instruments. So for example, NI, Elvis, EMONA, Datex. So do you see over here? This module is also a very similar kind of it. See, whatever we are trying to do with this, the same way we have done just now, because this is something as a DATEX board, data and telecommunication modules it is. So this is where we connect as a one of the top board to our Elvis module. So here, this is one. So where we have a different digital IOs over there, where we have a digital modules in it. So whatever we have as a multiplexer, input IO, a noise generator or amplifier here. So if you see in it, whatever these modules we have in it, whatever we have these modules in it. So when we choose something as a utilities, comparator, rectifier, diode with RC LPF and RC LPF, the same what we have here. This is the hardware unit earlier they used to give. So now what they made is, now they gave it in a form of a software one. The same thing which they have included in, the same thing which they have included as a module here. I think this one, yeah. The same thing they can include here. Noise generator. If you see there, where you have 3 different types of noise. So here also they have a 3 different types of noise. So noise generator and amplifier here added. So where you give signal as your input and where you can modify with that. So you have multiple different types of noise you have. So where you have a twin pulse generator, so where you can generate. Earlier, you have physical knobs over there where you can vary it to provide the delay or to change the width of the signal. So for multiplexers or multipliers, yes, you have a lot of things. So where earlier we used to get a patch cards to do this work. So you have a return to zero, non-return to zero. So when you want to have your uh, what to say is your PCM encoded signals if you want to plan for it. So these kind of encoding modules or PCI different types of signals where you can give over there. So the clock will be an input. From that EX, you will be giving an input to your encoder. The encoder output, you will take it output there. So here you have a master signal. The same way where you can take your master signal also there. So I have a multiplier 1. I have a PCM decoder. I have a PCM encoder. So now if you see there, these are the different I could say it is different labs where we can make it with I could say it is different hardware units, whatever we use here, the same thing which was available earlier in a form of a real hardware. So this is the Datex board. This is also from EMONA. So this one allows us to do a different kind of signals there or inputs where we can work with this. Now the same element which we got it in a, I could say it uh, as a remote lab where we got this module. Then if you see there, we have something as a SIGX module for signals and systems lab. So whatever you plan to do with this, the same thing you can do with here also. I open this image in a new place. So where if you see there, where we have a different signals to be generated. So where we have multiple elements where we connect. This is a top board on Elvis. So where you connect here. So if you see there, earlier whatever we have it is this module where we connected in place of this. So only thing is Elvis remains the same baseboard. These modules alone will change for us. So now they have it for Elvis 3 also. So this is what we are discussing there. So for Elvis 3, if you see for telecommunications, so we have this one. So this is for SIGX. And for Elvis 3, we have a telecommunication module. NI Elvis 3, EMONA communications module. So this is the board what we have there. So similarly, we remove this module, we connect a new one. So only this, if you see there, these modules will change. These modules will change. So rest of things all will work in the same fashion. So now, in a simple way, how I can tell you is, see, I have an NI Elvis hardware. See, now I have an NI Elvis hardware. So where I connected with this top board, I remove this top board, I add this module, I remove this top board, I add this module because I'll be doing different experiments with this. So one I'll use for the communication purpose, one I'll use, this is for the communication board where I have. So this is the communications board with NI Elvis. So this is for the Datex modules for a trainer kit purpose, what I use for elements. So I have one for EMONA Vortex also we have. Fiber optics also we have with this. EMONA fiber optics module there. This is the EMONA 3 for fiber optics. So I open image a new one. So now if you see there, I think this one would be a good one. So I zoom further. So now here also I have a coupler. So where I can generate different laser beams, so optical signals. So one for red and one for green. So where we have a coupler, where we can filter, where here we can combine two signal in a mixer. We can combine them red and green. We can give it to the filter. For example, in coupler we can couple red as well as green, and here we can give it to a filter where you can remove it out. So for a sequence generator, we can give this as an input over there, and where we can take it. Our outputs based on the signals. So this would be really an interesting example with our fiber optics trainer modules for it. See, the same kits are available for NI Elvis 2 and NI Elvis 3. See, earlier we used to do with NI Elvis 2 modules. So this old hardware. So these are the add-on boards. Do you see that? These are all NA Elvis 2 add-on boards where we added to it. Now the same modules we got replaced with NA Elvis 3 here, so that the same experiments we can conduct in a remote fashion. So now instead of getting this modules and add-ons boards with this, so we have a EMONA module, so which will help us to conduct the same kind of experiments. So with the help of same box, we can do a different experiments in a remote lab with this, so that this will be a really a convenient one where to do different lab based activities for us. I think now you can correlate with the NI Elvis and EMONA collaboration, how exactly we can use it for purpose of, I could say it as for the different lab solutions. So how exactly we could use it there. Any queries now? I shared my email ID. You can I just shared my details in chat. So if you have any queries or your lab related solutions, if you want to discuss, uh, you are free to give me a call or you can drop me an email. So where I can suggest you based on the lab setup which you are planning for it, whether you can go with a NetTims module, or where we can go for a software defined radio options also, where we have depends upon the lab we can provide for details. So where we have different lab utilities where we have with this. And one good thing is this particular I could say it is these SDR modules are programmable with GNE radio also, as well as they'll give you a software also with you, so where you can program with this. So we have another 15 minutes. I could leave for queries. If you have any queries, probably we can discuss on it.
Dear participant, if you have any doubts, any queries, do ask now, or you can type it in the chat box.
I hope you got some idea about how exactly we can have a present what to say is remote lab solutions convenient for our labs, and how NI and EMONA is collaborated for different lab solutions. So EMONA has their own solutions, and NI also has their own lab hardwares put together for uh, I could say it is for specific lab applications to be simplified. NI and EMONA have come closer together to give solutions with a 4text, DATEX, communications, and SIGX board experiments they have provided there at that. So now, colleagues,
I think no, sir. Sir, is it over? Shall we continue after lunch break?
what's up? Come again. Your voice is very low.
So is it over? Shall we continue after lunch break, sir?
Yeah, we can plan, but I just want to find out if anybody has any queries or
Yes, sir.
related any product
Let's wait for
related.
let's wait for a few more minutes, sir. After that, we can.
Sure, sir. We'll break by 12:50 to 12:55 so that we can have our lunch break and we can start.
Yes, sir. Sure, sir. Dear participant, if you have any queries, you ask now. Sir is available now. We'll wait for a few more minutes for your queries.
Hello, sir.
So, sir, tell me, sir.
Sir, I think we can wind up, sir.
Okay, sir. We will continue after lunch break. Sir.
Sure, sir, sure.
Okay. Dear participants, that will be the end of session. We will continue in the next session. The session links already been shared. Do join early 5 minutes. That will be the end of session. Thank you. We will continue at exactly 2 o'clock. Thank you. Thank you all.
Thank you, sir.
Thank you. Thank you, sir. We will continue for
Thank you
2
very much.
o'clock.
Thanks, everyone, for the time. If you have any queries, you just drop me a WhatsApp message or email so that I can help you out with the details.
Thank you, sir.
Sir, I take leave then.
That will be the end of. Okay, sir. Thank you, sir. Dear participant, that will be the end of session. We'll continue in the next session. Thank you. Thank you all.